A telescope pointed at a patch of sky the size of a grain of sand revealed thousands of galaxies. Some of them are so old, so massive, and so fully formed that they break every model we built to explain how the universe works. We expected to see baby galaxies, chaotic, dim, barely born. Webb showed us something else entirely. Galaxies that had no business existing that early. If you find that unsettling, subscribe, because what we found goes much deeper. Prepare yourselves, we begin. The image came back on July 12, 2022, and the room went quiet. NASA had promised something extraordinary. Decades of engineering, $10 billion, and a mirror the size of a tennis court, folded into a rocket and launched toward a point in space 1,000,000 miles from Earth. Astronomers have been waiting for this moment for over 20 years. They had their predictions ready, their simulations printed, their expectations firmly in place. And then the first image loaded. It showed a patch of sky so small that if you held a grain of sand at arm's length, that grain would cover it completely. Inside that grain of sky, there were thousands of galaxies, spirals, ellipticals, smeared arcs of light bent by gravity, galaxies so far away their light left before complex life existed anywhere we know of. All of it sharp, all of it real, all of it captured in roughly 12 hours of observation. The crowd applauded, but among the scientists, something else was happening underneath the celebration. The colors were wrong, the distances were wrong, the sizes were wrong. Several galaxies in that first image were already triggering quiet alarms in the minds of cosmologists who knew exactly what the numbers meant. Here is what they expected. When you look deep into space, you look back in time. Light travels fast, but the universe is vast. The light-reaching Webb from the most distant objects left its source billions of years ago. Astronomers expected that the further back they looked, the younger and messier everything would appear. Tiny protogalaxies, irregular clumps of gas just beginning to collapse, faint, chaotic structures, slowly pulling themselves together under gravity. That was the prediction, built on decades of theory, and confirmed, or so everyone thought, by the older Hubble Space Telescope. Webb's infrared eyes could see further and sharper than Hubble ever could. The plan was to confirm the model, fill in the gaps, and study the first generation of stars and galaxies forming in the infant universe. Instead, the images showed galaxies that looked ancient, structured, massive, fully assembled at distances that placed them impossibly early in cosmic time. One researcher described the experience as looking at a crime scene where the body is 100 years old, but the building it was found in was only constructed last week. The timeline refuses to add up. The James Webb Space Telescope sees an infrared light which is invisible to human eyes. This matters because the universe is expanding, and as it expands, light stretches. The further away a galaxy is, the more its light stretches into infrared wavelengths by the time it reaches us. Webb was designed precisely to catch that stretched light, to peer into an era Hubble could only glimpse at the edge of its vision. What Webb saw in those first hours was the beginning of a crisis in cosmology. Scientists did not panic publicly. Science rarely works that way. Papers began circulating. Teams started double-checking calibrations. Surely there was an error somewhere. A miscalculation, a contaminated dataset. The instruments were brand new after all. Maybe the redshift measurements needed refinement. Maybe the brightness estimates were off. But the checks came back clean. The numbers held. And the galaxies in that first image were exactly where they appeared to be. Something in our model of the universe was wrong. The question was how wrong. And as more images came in over the following months, it became clear that the first deep field was not an anomaly. It was a preview, because sitting inside that data, almost unnoticed at first, were galaxies so old they predated what physics said was possible. And understanding why requires going back to the very beginning of everything. Before Webb broke the model was beautiful. Cosmologists had spent decades building a precise, elegant picture of how the universe went from a hot, featureless explosion to the structured cosmic web we live inside today. It had a name: lambda cold dark matter. And for a long time, it worked almost perfectly. Here is how the story was supposed to go. The Big Bang happened roughly 13.8 billion years ago. For the first few 100 million years, the universe was a sea of hot gas, mostly hydrogen and helium, with no stars and no galaxies. Gravity was the only sculptor, and gravity, given enough time, pulls things together. Spread through that early gas was a mysterious substance called dark matter. You cannot see it, touch it, or detect it directly. But it has gravity, and that gravity created invisible scaffolding across the early universe. Regions where dark matter clumped slightly denser than their surroundings began pulling in regular matter, hydrogen and helium, toward them. Over tens of millions of years, that gas compressed, heated up, and eventually ignited into the first stars. Those first stars lived fast and died violently. Their explosions scattered heavier elements into the surrounding gas. More gas collapsed. More stars formed. Slowly, over hundreds of millions of years, clusters of stars began merging, growing, and organizing into the first primitive galaxies. The key word in that entire sequence is slowly. Galaxy formation, according to the model, is a gradual process. A galaxy the size of our Milky Way takes billions of years to build. It requires multiple generations of stars to live and die, countless mergers between smaller systems, and a steady accumulation of mass over cosmic time. You cannot rush it. The physics does not allow shortcuts. Astronomers knew this. They built it into every simulation they ran, and when they pointed Hubble into deep space and saw increasingly small, irregular, chaotic galaxies at greater distances, it confirmed what the model predicted. The universe looked younger the further back you looked. Exactly as expected. Webb was supposed to sharpen that picture, see the very first galaxies just beginning to flicker on, catch the earliest, messiest stages of galaxy formation in the act. Imagine you are watching a time-lapse of a city being built. You expect to see empty land first, then foundations, then half-finished buildings, then the completed skyline. Webb was designed to show us the empty land and the foundations. Instead, it found skyscrapers, fully built, fully lit, standing on land that, according to every clock we have, had only just been cleared. The problem is not just philosophical, it is mathematical. The universe has a speed limit for building structure. Dark matter needs time to clump. Gas needs time to cool and collapse. Stars need time to form, live, and die. You cannot compress those processes beyond a certain point without violating the underlying physics. And yet the galaxies Webb was finding seemed to have done exactly that. Some of them appeared at distances corresponding to only 300 million years after the Big Bang. That sounds like a long time. But on a cosmic scale, 300 million years is an eye blink. Our entire planet formed 4.5 billion years after the Big Bang, and the galaxy it sits inside had been building itself for billions of years before that. The galaxies Webb found at that early timestamp were enormous, bright, chemically complex, structured. Every one of those properties requires time the universe had not yet had. The model said these galaxies should look like scattered campfires. Webb found blazing cities, and the deeper astronomers looked, the stranger the story became. The paper landed in February 2023, and it sent a quiet shockwave through cosmology. A team of astronomers analyzing Webb's early data had identified 6 galaxies. Each one existed between 500 million and 700 million years after the Big Bang. Each one was enormous. One of them, if the measurements held, contained roughly as many stars as our entire Milky Way galaxy holds today. That alone was alarming. But what made the paper explosive was the phrase the lead researcher chose to describe the finding. He said these galaxies were so massive, so early, that they were, in his words, candidates for breaking the cosmological model entirely. Scientists rarely talk like that. To understand why those 6 galaxies caused such alarm, picture the standard cosmic timeline as a construction project on the world's tightest deadline. You have just received the keys to an empty plot of land. You have 300 million years to build a skyscraper. Every floor requires a specific sequence. Foundation first, structural frame next, floors poured in order, interior work last. You cannot skip steps, you cannot compress the schedule beyond what the materials allow. The galaxies Webb found were finished skyscrapers, standing on land that had barely been cleared. The mass of a galaxy carries a history inside it. Stars take millions of years to form. For a galaxy to contain hundreds of billions of stars, Those stars must have formed over an extended period, gone through multiple generations, and accumulated inside a gravitational structure large enough to hold them. Every shortcut you try to take in that process runs into a hard, physical limit. And yet, there they were. The team ran every check they could. They tested whether the galaxies were at a closer distance than the redshift implied, which would make them smaller and less alarming. The data held. They checked whether the brightness was being amplified by gravitational lensing, where foreground mass bends background light and makes it appear brighter than it is. Some amplification was present, but not nearly enough to explain the discrepancy. They checked whether the mass estimates themselves were somehow inflated by unusual star populations. The corrections were minor. After all checks, the galaxies remained enormous and ancient and early. One of the six carried a mass roughly 40 billion times greater than our own star. At the time it existed, the universe was roughly 4% of its current age. To put that in human terms, imagine meeting a fully grown adult who claims to be 4 years old. Clothes fitted, vocabulary intact, a career already in progress. The implications split astronomers into two camps almost immediately. One camp argued these galaxies proved the standard model, needed significant revisions, possibly a complete overhaul. The model's predictions for how quickly mass could accumulate into structures was clearly off. The question was how far off, and what the fix looked like. The other camp urged caution. Webb was a new instrument. Its calibrations were still being refined. The photometric redshifts being used to estimate distances, measuring color shifts across multiple wavelength bands rather than capturing a full spectral signature, carried uncertainties. It was possible, they argued, that some of these galaxies were closer than they appeared, but the spectroscopic confirmations began arriving. One by one, precise measurements locked in the distances. The galaxies were where the first estimates said they were. The model had a serious problem, and the 6 galaxies from that February paper were only the beginning of the evidence piling up against it. Size is everything. You can forgive a galaxy for being slightly brighter than expected, or slightly further along in its chemical evolution than the models predicted. Astronomy deals in estimates, and estimates carry error bars. But mass is different. Mass is the fundamental currency of cosmology. When the mass of an early galaxy comes back wrong, something deep in the model is broken. Here is why size matters so much in this context. Every galaxy in the universe grew by accumulating mass over time. That mass came from 3 sources: gas collapsing inward under gravity, stars forming from that gas, and smaller galaxies merging together to build larger ones. All 3 processes take time, long stretches of time, and they can only happen after dark matter has already formed the invisible skeleton that anchors the whole structure in place. Dark matter forms its scaffolding first, then regular matter falls in, then gas cools, then stars ignite, then those stars explode and enrich the gas with heavier elements. Then another generation of stars forms from that enriched gas. Each step depends on the previous one completing. You cannot overlap them significantly. The physics enforces the sequence like a locked door. Step 1 must finish before step 2 can begin. Our own Milky Way is a useful measuring stick. It contains somewhere between 200 billion and 400 billion stars. Astronomers estimate it took roughly 10 billion years to build to its current size. That timeline is consistent with the model. It lines up with the dark matter scaffolding, the merger history, the observed chemical gradients inside the galaxy. Everything fits. Now take one of the massive early galaxies Webb identified. Place it at a point in cosmic time when the universe was only 300 to 500 million years old. Give it a stellar mass comparable to the Milky Way, or in some cases, significantly larger. The model says that mass should require billions of years to accumulate. The universe at that point had been around for a fraction of that time. Imagine trying to fill a swimming pool using a garden hose, but someone tells you the pool was already full before you turn the hose on. The pool exists. The water is real. The hose cannot explain it. Some researchers tried to propose that early star formation ran faster than current models allow. Stars forming at rates 10, 20, even 100 times higher than anything we observe in the local universe today. That would compress the timeline. But it creates its own problems. Star formation at those extreme rates produces enormous amounts of radiation and stellar wind, which blows gas out of young galaxies and actually slows further growth. The fix breaks something else. Others suggested dark matter halos in the early universe clumped more efficiently than simulations predicted, giving gravity a head start on building structure. Possible. But the required efficiency pushes against observational constraints from the cosmic microwave background, the oldest light in the universe, which shows us how smooth and uniform matter was just after the Big Bang. The core problem, stripped down to its essentials: galaxies need time to get big. The universe did not have that time. And Webb keeps finding more of them. Each new confirmation adds weight to the same conclusion. Something about the early universe was fundamentally different from what the model assumed. The precise nature of that difference is still being argued, but one word keeps appearing in the papers: impossible. And the next discovery takes the impossibility even further. Astronomers had a name for it: the cosmic dawn. It referred to the era when the first stars switched on, somewhere between 100 million and 500 million years after the Big Bang. Before that moment, the universe was dark. Literally. No stars, no galaxies, just a thin fog of hydrogen gas, slowly cooling in the expanding blackness, and the invisible architecture of dark matter quietly pulling matter toward its densest points. The cosmic dawn was supposed to be the universe's rough draft, messy, tentative, the first fragile sparks of starlight in a universe-wide darkness, scattered and dim, struggling to hold together against the forces trying to tear them apart. Every simulation built to model this era produced similar results: small, irregular blobs of light, loosely organized collections of young stars, barely distinguishable from the surrounding gas, bright in ultraviolet light, because young stars burn hot and blue, but structurally simple, physically small. The first hesitant brushstrokes of a painting that would take billions of years to complete. Webb was pointed straight at that era, and the images that came back looked like someone had replaced the rough draft with a finished manuscript. One of the most striking findings involved not just individual galaxies, but the variety of galaxy types present at that early date. The standard model predicts a narrow range of structures during cosmic dawn. You expect young, irregular, gas-rich systems, possibly some early ellipticals beginning to take shape. The range of possible forms is limited because there simply has not been enough time for different evolutionary paths to diverge very far. Webb found spirals, disks, barred structures, smooth ellipticals already depleted of star-forming gas. All of these forms require either significant time to develop or specific physical processes that were not supposed to be operating at that early stage. One team examining a sample of early galaxies found that the structural diversity they observed matched what the standard model predicted for galaxies roughly 3 billion years more evolved. The early universe, according to Webb's images, looked several billion years older than it actually was. There is a useful way to picture this. Imagine receiving a photograph labeled as a newborn nursery. You look at it and see toddlers. Some of them are walking confidently. One appears to be reading. The label says 48 hours old. You check the hospital records. The date is correct. The children are real, and you have no explanation for how they got from newborn to toddler overnight. That is the experience Webb delivered to cosmologists studying the cosmic dawn. The trust signal here is important. The structural observations are confirmed. The distances are confirmed through spectroscopic measurements. The debate is entirely about what these confirmed observations mean for our theoretical models, not about whether the observations themselves are accurate. And the models are struggling. Simulation teams have been running new versions of their programs with adjusted parameters, trying to reproduce what Webb sees. Some come close, none fully match the data. To reproduce the observed diversity and structural maturity of cosmic dawn galaxies, the simulations require conditions that do not match other confirmed observations of the early universe. Something is genuinely, measurably off, and one specific galaxy, confirmed in 2024, pushed the strangeness to a level that forced even the most cautious cosmologist to stop and pay attention. In October 2024, astronomers announced a confirmation that rewrote the record books. A galaxy designated as the most distant spectroscopically confirmed object ever observed had its distance locked in. The light reaching Webb from this galaxy left its source roughly 13.4 billion years ago. The universe at that moment was only 300 million years old. 2% of its current age. The galaxy itself is not enormous by modern standards. Compared to the giants that dominate today's universe, it is relatively compact, but that is almost beside the point. The unsettling thing about this galaxy is its light. Specifically, the kind of light it is producing. When astronomers analyzed the spectrum of this galaxy, they found strong emission lines indicating active, vigorous star formation. Stars were forming inside this galaxy at a rapid rate. That alone is expected for young galaxies. Young galaxies burn fast, but alongside the star formation signal, there were also chemical signatures, evidence of elements heavier than hydrogen and helium already present inside this galaxy. Heavier elements, everything beyond hydrogen and helium on the periodic table, only form inside stars. They are forged in stellar cores over millions of years and released into space when those stars explode. For a galaxy at this distance, at this age, to already contain detectable quantities of heavier elements, it means that at least one full generation of stars had already lived, burned through its fuel, and died before this galaxy even appears in our data. That chain of events takes time, minimum tens of millions of years, possibly longer, and this galaxy already existed at 300 million years after the Big Bang, which means the stellar generation before it, the one that produced those chemical signatures, had to have formed and completed its entire life cycle even earlier. We are looking at evidence of a generation of stars we have never directly observed, whose existence we can only infer from the chemical fingerprint they left behind. The light from this galaxy is unsettling precisely because it is a message written by things that no longer exist, transmitted across a distance so vast that by the time we received it, entire civilizations could have risen and collapsed in the time the signal was traveling. And the message says, we were already here. We had already lived. The story started before the chapter you thought was the first one. The confirmed distance, combined with the chemical signatures, sets a hard lower limit on how early star formation must have begun in at least some regions of the early universe. Earlier than any simulation running before Webb's launch predicted. This galaxy is a clue, a piece of evidence pointing at something we have not yet identified. Some process in the very early universe that compressed the timeline of stellar evolution far beyond what the models allow. There is a theory about what that process might involve. It requires imagining a kind of star that no longer exists anywhere in the observable universe. A kind of star so massive, so bright, and so violent that it reshaped everything around it in an extremely short period of time. That story comes next. Before going further, there is one concept worth understanding clearly, because almost every impossible galaxy Webb has found depends on one measurement tool, and understanding that tool is what makes the impossibility real rather than abstract. The tool is redshift. Here is how it works. Light travels as a wave, like a sound wave. Its frequency determines how we perceive it. High-frequency light appears blue to our eyes. Low-frequency light appears red. When a light source moves away from you, the waves stretch out, shifting toward the red end of the spectrum. When it moves toward you, they compress, shifting toward blue. This is the same effect that makes a passing ambulance's siren drop in pitch as it moves away. Now apply that to the universe. Every galaxy beyond our local group is moving away from us because space itself is expanding. The further away a galaxy is, the faster it is receding and the more its light stretches. By the time light from the most distant galaxies reaches Webb's mirror, it has stretched so far beyond visible wavelengths that it only exists in infrared. That is precisely why Webb was built with infrared detectors. The amount of stretching is called the redshift value. A redshift of 1 means the light's wavelength has doubled since it was emitted. A redshift of 10 means it has stretched to 11 times its original wavelength. Astronomers use this value as a distance ruler. By measuring how much a galaxy's light has stretched, they can calculate how far away it is, and therefore, how long ago that light was emitted. When Webb began returning redshift measurements for early galaxies, many came back with values between 8 and 16. Each step up that scale corresponds to an earlier and earlier period in cosmic time. A redshift of 10 puts a galaxy at roughly 450 million years after the Big Bang. A redshift of 14 pushes it back to around 300 million years. The confirmed galaxy from the previous chapter carries a redshift value above 14. Now here is where the impossibility becomes precise. The early measurements of many Webb targets came back as photometric redshifts. These use multiple images of the same galaxy taken at different wavelengths to estimate the redshift, essentially triangulating the answer from the shape of the light curve. They are fast and useful, but they carry error ranges. The spectroscopic conformations are the gold standard. They spread the galaxy's light into a full spectrum and identify specific chemical fingerprints. Those fingerprints only appear at exact wavelengths in the lab. How far they have shifted from those exact wavelengths gives a precise confirmed redshift value. When spectroscopic confirmations started coming in for Webb's early galaxy candidates, the expectation inside the community was that some of the most extreme photometric estimates would soften. The error bars would shrink toward more reasonable distances. The most alarming cases would turn out to be closer than initially measured. The opposite happened. Several targets came back with confirmed redshifts, at or exceeding the photometric estimates. The galaxies were as far away as feared, or further, and at those distances, with those confirmed ages, their masses and brightness levels remained as alarming as the first measurements suggested. The ruler works. The distances are real. The numbers are not coming back wrong because of measurement error. They are coming back impossible because the universe in its early chapters behaved in ways our model did not predict. And the next layer of strangeness does not involve distance at all. It involves what is inside these galaxies. Specifically, the age of the stars already living in them when Webb caught their light. This is the detail that stopped many researchers cold. When Webb analyzed the light from some of the earliest confirmed galaxies, the spectral signatures revealed something unexpected inside them. Alongside young, hot blue stars, there were old stars. Red, cool, evolved. Stars that had already burned through the fast, bright phase of their lives and settled into their long, slow decline. Old stars require time to become old. That sounds obvious, but the implication is severe. A young star burns hot and emits mostly blue and ultraviolet light. As it ages over millions to billions of years, depending on its mass, it swells, cools, and shifts toward red wavelengths. The presence of these red evolved stellar populations inside a very early galaxy means those stars had already gone through a significant portion of their lives before Webb captured the galaxy's light. Think of it this way. You are looking at a photograph of a crowd taken at a high school. Some of the people in the photograph are clearly elderly. Grey hair, lined faces. If the school only opened last year, something is deeply wrong with your understanding of when these people were born. That is the logical structure of what Webb found. Galaxies that were themselves young, measured by their distance and confirmed age in the universe, but already containing stellar populations old enough that they should not have had time to age that far. In several cases, astronomers estimated that the red stellar populations inside these early galaxies were already hundreds of millions of years old at the time the observed light was emitted. Some estimates pushed further. Possibly as much as 1 billion years of stellar evolution had occurred inside galaxies that existed in a universe younger than 1 billion years. The overlap is nearly impossible. This finding directly affects something called stellar archaeology, the practice of reading a galaxy's history from its current stellar population. Astronomers use the mix of stellar ages inside a galaxy as a record of its past. A diverse mix with both very old and very young stars tells a long history. A galaxy dominated by young stars tells a short one. Early galaxies by the standard model should tell very short histories. They have not had time to accumulate multiple generations of stars. Webb found several telling histories that required more time than the universe had provided. The confirmed presence of evolved stellar populations at these redshifts is one of the most difficult observational results for current models to explain. The models require either a radically accelerated rate of early star formation, with stars forming and aging in compressed timescales, or an earlier origin for structure formation than the model currently places. Neither solution is simple. Both require revising fundamental assumptions, and this was not even the most unsettling version of the old stars problem. Some early galaxies did not just contain old stars, they had stopped forming new ones entirely. Galaxies that had gone completely quiet, no star formation, no gas, no activity, just a population of aging stars cooling slowly in the dark. Those galaxies have their own name and their own deeper mystery. They have a nickname in the field, red and dead. It sounds almost poetic, but the reality is cosmologically disturbing. A red and dead galaxy is one that has exhausted its supply of star-forming gas and gone quiet. No new stars forming, no ultraviolet glow from hot young stellar populations. Just a sea of old, cool, red stars slowly fading over billions of years. In the local universe, the galaxies we live near today, red and dead systems are common. They are usually massive elliptical galaxies that used up their gas long ago and settled into a calm, aging existence. The problem is when they appear. In the local universe, a galaxy becoming red and dead makes sense. It has had 10 billion or more years to form stars, exhaust its gas supply, and go quiet. The timeline is entirely reasonable. You built the whole house, you moved in, you used up all the building materials. Now you just live there. Webb found red and dead galaxies at distances corresponding to just 700 million to 1 billion years after the Big Bang. A galaxy that has gone red and dead has to have first formed, then vigorously formed stars at a high rate for an extended period, then somehow lost or expelled all of its remaining star-forming gas, and then gone quiet. That entire sequence from first star formation to complete cessation takes time. Based on what we observe in the local universe, that process typically spans several billion years. At 700 million years after the Big Bang, the universe had not yet been around for several billion years. One confirmed example, reported by a team using Webb spectroscopic data, showed a galaxy that had already completed its entire active star-forming lifetime and gone quiet. The analysis suggested this galaxy had formed the bulk of its stars in a burst lasting only 30 to 90 million years, an extraordinary rate. Then it stopped, completely. And it was already dead at a cosmic age when, according to the standard model, galaxies should still be in their most active growth phases, 30 to 90 million years to form an entire galaxy's worth of stars, and then go permanently dark. For comparison, our star took roughly 50 million years to form alone. This galaxy formed hundreds of billions of stars in roughly the same time frame. The intensity required is almost incomprehensible. There is a mechanism that can drive a galaxy quiet. Feedback from a supermassive black hole at its center. When a black hole grows large enough and feeds actively enough, it blasts energy and radiation into the surrounding galaxy, with such force that it heats and disperses the star-forming gas, shutting down stellar nurseries across the entire system. This process, called quenching, is observed in the local universe and is a standard part of galaxy evolution models. But those models place quenching late in galaxy evolution, after a long period of black hole growth. At 700 million years after the Big Bang, the black holes themselves should still be small, too small to quench an entire galaxy, unless the black holes were already enormous. And that is exactly what Webb found next. The backbone of every galaxy is invisible. You cannot photograph dark matter. You cannot weigh it directly. Every detector ever built to catch a dark matter particle has come up empty. And yet cosmologists are deeply confident it exists, because without it, nothing in the universe makes structural sense. Galaxies spin in ways that require far more mass than their visible stars can provide. Galaxy clusters bend light in ways that demand invisible mass. The entire large-scale structure of the cosmic web, the vast network of filaments and voids that organizes the universe, matches simulations only when dark matter is included. Under the standard model, dark matter is the first actor in the galaxy formation story. In the hot, early universe, dark matter began clumping into what cosmologists call halos, invisible knots of gravitational influence. These halos formed the anchor points around which regular matter could collect. Gas fell into the halos, cooled, and eventually collapsed into stars. First the dark matter structure, then the stars. The halo forms first. Everything else follows. Here is the critical constraint that makes Webb's discoveries so troubling. The size of a dark matter halo limits how much regular matter can collect inside it. You cannot build a massive galaxy inside a small halo. The gravitational depth of the halo determines the ceiling. And in the early universe, halos were small because they had not yet had time to grow through their own mergers and accretion. The Standard Model's predictions for halo mass at early cosmic times set a firm upper limit on how massive galaxies could be at any given period. It is a physical ceiling enforced by gravity, expansion, and time working together. The model does not predict this limit as a rough estimate. It calculates it precisely. Webb's massive early galaxies exceed that ceiling. Some teams have estimated that producing the observed galaxies within standard lambda cold dark matter would require the conversion of nearly 100% of available gas into stars. Every single atom of gas inside those dark matter halos would need to have formed a star. No waste, no outflows, no gas lost to radiation or feedback. Perfect efficiency. Observed star formation in the local universe operates at efficiencies of a few percent, sometimes reaching 10% under extreme conditions. Perfect efficiency has never been observed anywhere. It may be physically impossible. So either the efficiency assumption is wrong by an enormous margin, or the halos themselves were larger than the model predicts at that epoch, or matter assembled into structure faster than the standard timeline allows. One emerging idea suggests that in the very early universe, the behavior of dark matter itself might have been different. The standard model treats dark matter as cold, meaning it moves slowly and clumps easily. Some researchers argue that under certain early universe conditions, dark matter could have organized into denser structures faster than current models account for, effectively giving galaxy formation a significant head start. This idea is a theory, not yet confirmed by independent observation, but it addresses the waiting period that the data seems to have erased. Under the standard model, galaxies wait for their dark matter halos to mature before they can grow. Webb's galaxies appear to have skipped that wait entirely, as if the scaffolding appeared fully built and the construction began simultaneously, defying the sequence the model demands. The structure beneath the structure failed to slow things down, and that failure points directly towards something that was supposed to grow gradually, something that had no right to be enormous this early: the black holes. Every large galaxy contains a supermassive black hole at its center. That fact is confirmed across thousands of observations. Our own galaxy has one, sitting roughly 26,000 light-years from where you are right now. It contains the mass of roughly 4 million stars compressed into a single point. And by galactic standards, it is considered modest. The supermassive black holes at the centers of some galaxies reach masses of billions of stellar masses. The most extreme confirmed examples push toward tens of billions. These are the gravitational engines that sometimes power the brightest objects in the universe, blazing cores called quasars, where infalling matter heats to extreme temperatures and blazes across billions of light years. Under the standard model, supermassive black holes grow gradually. They start as smaller black holes, potentially remnants of the first generation of massive stars, and accumulate mass over time by swallowing gas, dust, and other matter. The growth is bounded by something called the Eddington limit, a natural ceiling on how fast a black hole can feed before the radiation it produces pushes infalling matter back out. At the Eddington limit, a black hole can roughly double its mass over roughly 45 million years. That sounds fast, but to grow from a stellar mass black hole of perhaps a few hundred solar masses to a supermassive black hole of 1 billion solar masses requires roughly 1 billion years of sustained feeding at the Eddington limit. That is the minimum timeline, with no interruptions and maximum possible efficiency. Webb found a quasar, an actively feeding supermassive black hole, at a distance placing it just over 600 million years after the Big Bang. The black hole powering it had already accumulated a mass of roughly 1.6 billion solar masses. 600 million years into a process that takes a minimum of 1 billion years. One analysis put the problem bluntly. If this black hole formed from a stellar mass seed and fed continuously at the Eddington limit from the first possible moment after the Big Bang, the math still does not reach the observed mass in the available time. There are proposed solutions. One involves what cosmologists call heavy seeds. The idea that in the very early universe, some regions of dense gas collapsed directly into black holes with masses of tens of thousands to hundreds of thousands of solar masses, skipping the stellar phase entirely. This direct collapse scenario bypasses the slow growth problem by starting with a dramatically larger seed. Direct collapse is a theory, a compelling one, supported by some indirect evidence. But astronomers have not yet directly observed a direct collapse black hole in formation. Webb is searching for them. Another proposal involves periods of super-Eddington accretion, where a black hole feeds beyond the theoretical limit during brief intense episodes. Some observations in the local universe hint this may occur, but sustained super-Eddington growth over cosmic timescales remains unconfirmed. The confirmed fact is this: Webb has found supermassive black holes that are too massive for the time they occupy. Multiple examples, at multiple distances, all confirmed spectroscopically. And those black holes may be responsible for something even more baffling about the early universe's brightest galaxies. Light tells stories. The brightness of a galaxy tells you how many stars it has, how actively it is forming new ones, and roughly what kind of stellar population it contains. Astronomers have calibrated these relationships carefully over decades, measuring thousands of galaxies across cosmic time. The relationship between mass and brightness, called the mass-to-light ratio, is one of the most reliable tools in observational cosmology. Webb broke it. When astronomers measured the brightness of early galaxies and compared it to their estimated masses, the numbers came back wrong. The galaxies were too bright, significantly systematically too bright across a large sample. Some were producing between 5 and 10 times more ultraviolet light than their estimated stellar masses should allow. A galaxy generating 10 times more light than its mass predicts is not a calibration issue. It is a statement about physics. Either the mass estimates are severely wrong, or the stars inside these galaxies are producing light far more efficiently than stars do anywhere in the local universe. The first option, wrong mass estimates, was investigated carefully. Mass estimates for distant galaxies rely on modeling the spectral energy distribution, the total light output across all wavelengths, and comparing it to stellar population models. These models have uncertainties, but those uncertainties are well characterized. The excess brightness in Webb's early galaxies exceeded the uncertainty ranges by significant margins. The second option leads somewhere genuinely interesting. Stars produce light through nuclear fusion. The efficiency of that process depends heavily on the mass and chemical composition of the star. Massive stars burn hotter and brighter relative to their mass than smaller stars do. And the chemical composition matters because heavier elements, anything beyond hydrogen and helium, affect how energy moves through a star's interior, and ultimately how much light escapes. The very first stars in the universe, formed from pure hydrogen and helium before any heavier elements existed, would have been fundamentally different from any star alive today. More massive, on average. Hotter. Far more luminous per unit of mass. They are called population 3 stars, and astronomers have been searching for direct evidence of them since the concept was first proposed. Webb has not yet directly observed a population 3 star, but the excess brightness of early galaxies is one of the strongest indirect signals that these extreme early stars may have dominated the first generations of stellar populations. Galaxies packed with population 3 stars would blaze with light far beyond what their mass would predict under current stellar models. This is still a leading theory, confirmed by multiple independent teams as a plausible explanation for the luminosity excess. Direct confirmation awaits deeper observations. But the brightness problem does more than hint at unusual stars. It exposes a crack in the standard model, wide enough to drive a significant theoretical revision through. And that revision, when it comes, will have to confront not just the brightness numbers, but the specific type of light these galaxies are pouring into space. Because the most dramatic signal is not visible light, it is ultraviolet. And the ultraviolet output of early galaxies is the single most disruptive measurement Webb has delivered. Picture the universe at 100 million years old. No stars yet, no galaxies, just hydrogen and helium gas, cooling slowly in the dark, falling toward the densest knots of dark matter gravity, had spent millions of years building. The first gravitational traps are set. The gas is beginning to compress. Now picture that gas igniting. The first stars in the universe formed from material unlike anything that exists today. Pure hydrogen and helium, with no heavier elements mixed in. No carbon, no oxygen, no iron, nothing that modern stars contain in small but significant quantities. This chemical purity had a profound physical effect on how those stars formed. In modern star formation, heavier elements act as cooling agents. When gas clouds collapse under gravity, they heat up. Heavy elements radiate that heat away, efficiently, allowing the cloud to cool and fragment into smaller pieces, which each collapse into individual stars of modest mass. The heavy elements put a natural brake on how big any single star can grow. Without those heavy elements, the early gas clouds could not cool efficiently. They fragmented less. The pieces that collapsed were larger, far larger. The result, according to theoretical models, was stars of extraordinary mass, potentially hundreds of times the mass of our own star. Some models predict these population 3 stars could have reached thousands of solar masses, though this remains actively debated. At those masses, they would have burned at temperatures and luminosities that dwarf anything observable in the modern universe. A single population 3 star could have outshone entire young galaxies, and they would have lived fast. The most massive stars burn through their fuel quickly. A star with 100 times average mass might exhaust itself in a few million years, compared to the billions of years a modest star like ours spends on the main sequence. Population 3 stars would have blazed, exploded as the most powerful supernovae ever seen, and seeded the universe with the first heavy elements, all within an eye blink of cosmic time. Their deaths would have been as important as their lives. Those supernovae scattered carbon, oxygen, nitrogen, and heavier elements into the surrounding gas for the first time. The next generation of stars formed from that enriched gas, and the generation after that, each explosion adding more complexity to the chemical inventory of the universe. This is why the chemical signatures Webb finds in early galaxies matter so much. Every detection of heavy elements at extreme distances is evidence of population 3 stars doing their work. We read their biography in the debris they left behind. Webb has not yet captured a confirmed image of a population 3 star. They are almost certainly extinct. The universe ran out of chemically pristine gas long ago, and no region is known to contain the conditions needed to form them today. What Webb is hunting for are galaxies so early, so close to the first light, that their spectra show the characteristic emission signatures of population 3, stellar populations. Several candidate signals have appeared in Webb's data. A few are intriguing enough that dedicated follow-up observations are underway. Confirmation would be among the most significant discoveries in the history of astronomy, and the importance extends well beyond astronomy. Population 3 stars are the origin story of every atom of carbon, oxygen, and iron in your body. The elements that make complex chemistry and life possible did not exist until those first enormous stars died. The universe needed them to fail spectacularly before anything like us was ever possible. That debt runs in both directions, and the evidence for how it was paid is reshaping a theoretical framework that had stood unchallenged for decades. For roughly 30 years, one theoretical framework has dominated cosmology: the lambda, cold, dark matter model. Cosmologists call it lambda CDM. It describes how the universe evolved from the Big Bang to today, incorporating dark matter, dark energy, the expansion of space, and the formation of large-scale structure. It makes precise predictions, and across an enormous range of observations, it has held up with remarkable accuracy. The cosmic microwave background, the oldest light in the universe, matches lambda CDM predictions to extraordinary precision. The distribution of galaxies across vast cosmic distances matches the model's predictions for how matter clustered under gravity over billions of years. The abundance of light elements in the universe matches the model's predictions for what the Big Bang should have produced. Across these and many other tests, lambda CDM performed like a well-calibrated instrument. Then Webb started returning data from the early universe. The tension between Webb's observations and lambda CDM predictions is real, confirmed, and currently unresolved. The question is whether it represents a need for small adjustments within the existing framework, or a signal that the framework itself requires fundamental revision. The adjustments camp argues that some parameters within lambda CDM can be tuned to accommodate early galaxy formation. Perhaps star formation efficiency was genuinely higher in the early universe. Perhaps some feedback mechanisms operated differently under early universe conditions. The model allows some flexibility, and these adjustments might be enough to close the gap. The revision camp argues the gap is too wide. The sheer number of confirmed massive early galaxies, the presence of evolved stellar populations at extreme distances, the brightness excess, the oversized black holes, and the red and dead systems all point in the same direction. The early universe formed structure faster, more efficiently, and more completely than lambda CDM predicted. And the deviation is not marginal. One useful analogy is a clinical trial where the results come back consistently outside the predicted range. A single outlier gets noted. 5 outliers trigger a review. 10 consistent outliers in the same direction force a re-examination of the original hypothesis. Webb has returned dozens of outliers, and they are nearly all in the same direction. The early universe was more mature than the model allowed. The confirmed fact is that lambda CDM, in its current form, does not reproduce Webb's early galaxy observations without modifications. That is agreed upon by essentially all researchers in the field. The debate is entirely about the magnitude and nature of those modifications. And sitting beneath that debate is a deeper question, a question that cuts to the heart of what we think we know about the origin of everything. The question is whether lambda CDM is failing because it needs parameter adjustments, or because one of its core components, dark energy, dark matter, or the assumption that physical constants were the same in the early universe as they are today, was wrong to begin with. Some cosmologists have begun looking at that last possibility very seriously, and what they are finding, piece by piece, may reframe every answer Webb has provided. Science rarely breaks loudly. The textbooks do not get rewritten overnight. The model does not collapse in a single press conference. What actually happens is a quieter process. A small group of researchers begins circulating a paper that makes an uncomfortable argument. Other researchers read it with skepticism. They try to find the error. They cannot quite find it. A few more papers appear, reaching the same conclusion from different angles. The argument begins gathering weight. That is the process currently underway in cosmology. The argument is specific. Galaxy formation in the early universe ran significantly faster than the standard model allows. The evidence for this conclusion comes from multiple, independent measurement techniques, applies to a statistically significant sample of objects, and survives the calibration checks that were supposed to explain it away. The uncomfortable implication is that something about the early universe's physical environment differed from what lambda CDM assumes. Several specific proposals have emerged. One involves the behavior of dark matter at early times. Standard lambda CDM treats dark matter as cold and collision-free, meaning it does not interact with itself or with regular matter, except through gravity. But some models of dark matter allow for weak self-interactions. Even a small level of dark matter self-interaction could cause it to clump more efficiently in the early universe, building larger halos faster and giving galaxy formation a significant head start. This idea, called self-interacting dark matter, has been around for decades, but Webb's observations have pushed it back to the center of discussion because the head start it provides is exactly the kind needed to reconcile the early galaxy masses with an otherwise intact cosmological timeline. Another proposal revisits the concept of primordial black holes. Under certain early universe conditions, density fluctuations in the hot plasma of the infant universe could have been large enough to collapse directly into black holes before any stars formed. These primordial black holes, if they existed with the right mass distribution, could have seeded the formation of early galaxies more efficiently than dark matter halos alone, providing both the gravitational anchor and the central black hole seed simultaneously. Primordial black holes are a theory with ongoing observational tests. Webb itself is part of those tests, searching for specific signatures that would confirm or rule out the primordial black hole scenario for galaxy seeding. A third group of researchers has taken a more radical position. They argue that the star formation rate in the early universe was simply higher than any local observation would suggest, driven by conditions that no longer exist. Dense, metal-poor gas under extreme gravitational compression in halos more concentrated than lambda CDM predicts, could have formed stars with an efficiency approaching values the model treats as physically unreachable. Each of these proposals touches a different piece of the standard model. Each is a targeted adjustment rather than a wholesale replacement. But they all share a common feature. They require the early universe to have operated under conditions meaningfully different from those the standard model assumes. And one of the most striking pieces of evidence for that difference is not in the galaxies themselves, it is in what sits between them. A discovery so geometrically wrong, so spatially impossible at its confirmed distance, that it forced an entirely separate line of theoretical emergency. Galaxy clusters are the largest gravitational structures in the universe. Collections of hundreds or even thousands of galaxies, bound together by gravity and embedded in vast clouds of superheated gas, sitting inside enormous dark matter halos that can span tens of millions of light years. They are the endpoints of cosmic structure formation, the biggest things gravity has ever built, and they take a very long time to build. Under lambda CDM, the timeline for cluster formation is well established. Small dark matter halos form first. They merge into larger halos. Those larger halos merge again. Over billions of years, this hierarchical process builds progressively larger structures, culminating eventually in the massive clusters observed in the local and intermediate distance universe. The process is slow by design. Gravity is patient. Mergers take time. The earliest galaxy clusters in the standard model should appear at roughly 2 to 3 billion years after the Big Bang. Before that, the structures needed to anchor a full cluster simply have not had time to grow through the required sequence of mergers. Webb found a confirmed protocluster, a bound, collapsing structure containing multiple massive galaxies, on track to become a full cluster, at a distance placing it at roughly 800 million years after the Big Bang. 800 million years, more than a billion years before the model's earliest predicted cluster formation time. The structure contains several spectroscopically confirmed galaxies within a small region of space, moving with velocities consistent with gravitational binding. The galaxies themselves were already massive. The gas surrounding them showed the early signs of the superheated intracluster medium that defines mature clusters in the local universe. Everything about the structure read as a cluster at an age when clusters should not have existed. The dark matter halo required to produce this structure at this distance, according to calculations run by multiple independent teams, would have needed to reach a mass roughly equivalent to a quadrillion times the mass of our own star, all within 800 million years. Under standard lambda CDM, halos of that mass are simply not predicted to exist that early. The mergers needed to build them had not had time to complete. One team described the situation as finding a fully formed mountain range on a planet that had only just cooled from molten rock. The timescale for the geology does not fit the age of the terrain. The cluster finding amplifies every concern raised by individual early galaxies. Galaxy formation being anomalously fast could in theory be explained by local conditions. Unusual gas concentrations, rare but possible density peaks in the early universe. But a full protocluster requires coordinated large-scale structure formation across a volume of space hundreds of millions of light years across. Local explanations do not reach that scale. The finding requires the large-scale matter distribution of the early universe to have been more concentrated, more organized, and more advanced than lambda CDM's initial conditions predict. That goes beyond galaxy formation physics and touches the very starting conditions of the universe. And there is one more structural finding from Webb that deepens the problem further, because it is not just the size and age of early galaxies that the model gets wrong, it is their shape. And the shape problem turns out to be one of the strangest pieces of evidence yet. Simulations predicted chaos. When cosmologists modeled the very first galaxies forming in the early universe, the results were consistent across virtually every simulation platform. Young, early galaxies should be irregular, chaotic, asymmetric structures. Blobs of star formation loosely organized around gravitational centers, constantly disrupted by mergers, gas inflows, and violent stellar feedback. The smooth, ordered shapes that characterize galaxies in the local universe, spirals with elegant arms, smooth ellipticals with clean light profiles, were supposed to be the product of billions of years of gravitational settling and quiet evolution. Early galaxies, by every prediction, should look like the universe's rough drafts. Webb showed something different. When astronomers began analyzing the morphologies, the structural shapes of early galaxies in Webb's images, they encountered a population dominated by a specific form: flat, elongated disks, not the rotationally symmetric spirals of mature galaxies, but thin, extended structures, like a lens or a flattened oval, with the bulk of their stellar mass arranged along a single plane. This form, sometimes called a prolate or oblate disk, depending on the specific geometry, was found in a significant fraction of early galaxies across multiple Webb survey programs. One survey found that thin disk structures made up a substantially larger share of early galaxy morphologies than any simulation had predicted. The problem with these disks is not just their existence, it is their implied history. A flat, ordered disk requires the gas that formed it to have settled into a coherent rotation pattern. Gas falling into a dark matter halo from multiple directions, as it does in simulations, produces irregular, chaotic structures. To produce a thin disk, the infalling gas must have some degree of organized angular momentum to begin with, meaning it must have been rotating in a broadly consistent direction before it ever reached the galaxy. In the standard model, the angular momentum of infalling gas at early times is expected to be disordered, coming from many directions across a chaotic young universe. The smooth disks Webb found require early universe gas to have been more ordered, more coherent in its rotational structure than the model predicts. Several explanations are under investigation. One involves the role of cosmic filaments, the thin strands of dark matter and gas that connect galaxy clusters in the large-scale cosmic web. Simulations show that gas flowing into forming galaxies along these filaments tends to carry more coherent angular momentum than gas accreted from random directions. If early galaxies were embedded in a more developed filamentary network than standard models predict, the disk morphologies might follow naturally. But this explanation requires the cosmic web itself to have been more organized at early times than lambda CDM predicts. Another piece of structure arriving ahead of schedule. There is a second morphological finding that cuts even deeper than the disks. Because among the flat, elongated structures Webb catalogued in the early universe, several showed something that had no business being there at all: spiral arms. Fully developed, sweeping spiral structures in galaxies existing at a time when the standard model says spiral formation had barely begun. And the implications of those arms reach into the deepest assumptions of how galaxies evolve. Spiral arms take time. That is not an assumption. It is a physical consequence of how disk galaxies work. A spiral arm is a density wave, a region of compressed gas and stars that sweeps through a rotating galactic disk like a slow-moving traffic jam on a circular highway. The cars keep moving through the jam, but the jam itself persists. For that wave pattern to establish itself, the disk must have been rotating long enough for the density pattern to organize, reinforce, and stabilize across the full width of the galaxy. Estimates for how long that process takes in the local universe range from several 100 million to over 1 billion years after a disk first forms. You need the disk first. Then you need it to rotate. Then the wave pattern gradually emerges from small gravitational perturbations as the disk matures. Webb found spiral structure in galaxies at distances corresponding to less than 1 billion years after the Big Bang. One confirmed example, identified in early Webb survey data, showed clear spiral features at a redshift placing it roughly 2 to 3 billion years after the Big Bang. That was already surprising, but deeper surveys pushed the finding further back. Candidate spiral structures began appearing at redshifts corresponding to under 1 billion years of cosmic age. Some of the most extreme candidates sit at distances where the universe was younger than the minimum formation time for spiral arms, according to the standard timeline. The confirmed cases at 2 to 3 billion years are already difficult for current models to explain. At those distances, simulations predict that most disk galaxies should still be in the irregular turbulent phase that precedes spiral development. Finding ordered spiral structure that early requires either the disk formed earlier than the galaxy's observed redshift implies, or the spiral formation process ran faster than any simulation has reproduced. The deeper candidates, the ones at under 1 billion years, are currently classified as high-priority targets for spectroscopic follow-up. If confirmed, they would represent the single most structurally mature objects ever observed at those distances. The significance extends beyond the structural question. Spiral arms are not just aesthetically striking. They are engines of star formation. The density wave compresses gas as it passes through, triggering bursts of star formation along the arm. A galaxy with functioning spiral arms is a galaxy with a self-sustaining cycle of stellar birth built into its architecture. If early galaxies had functional spiral arms, they had access to an efficient self-organizing star formation mechanism far earlier than the model allows, which would help explain at least partially why they accumulated stellar mass so quickly. But it raises its own question. Spiral arms are fragile. Mergers destroy them. Violent gravitational interactions from neighboring galaxies disrupt the density wave pattern. In the early universe, where galaxy mergers were far more common than today, maintaining an ordered spiral structure should have been nearly impossible. And yet, ordered, sweeping, present, the shapes Webb is finding in the early universe keep telling the same story from different angles. Structure arrived ahead of schedule. Order appeared where chaos was predicted. Something in the earliest chapters of cosmic history ran faster, smoother, and more efficiently than the model that was supposed to describe it. And the evidence for that early efficiency is written not just in the shapes of galaxies, but in their chemistry. Inside these ancient systems, a periodic table is already filling in, element by element, and the timeline it implies is deeply unsettling. Every element heavier than helium was built inside a star. That sentence contains an entire origin story. Carbon, oxygen, nitrogen, iron, calcium, every atom that makes up the ground beneath your feet, the air in your lungs, and the cells in your body was forged inside a stellar core over millions of years and then scattered into space when that star died. The universe started with only hydrogen, helium, and trace amounts of lithium. Everything else on the periodic table had to be manufactured, element by element, through generations of stellar birth and death. This process has a pace. Stars take millions of years to form, live, and explode. Each generation enriches the surrounding gas slightly. The next generation forms from that slightly richer gas, and so on. Astronomers call this chemical enrichment, and it accumulates slowly across cosmic time. When Webb analyzed the spectra of early galaxies, some of them showed chemical enrichment levels that required multiple stellar generations to produce, at distances corresponding to less than 1 billion years after the Big Bang. One confirmed case involved a galaxy whose spectrum showed oxygen abundance approaching levels comparable to galaxies in the local universe. Galaxies that have had over 10 billion years to enrich themselves chemically. This particular early galaxy had managed comparable enrichment in a fraction of the time. The oxygen abundance is especially diagnostic, because oxygen is produced primarily in the cores of massive stars during their lifetimes, and released in supernova explosions. The quantity of oxygen in a galaxy's interstellar gas directly reflects how many massive stars have formed, lived, and died inside it. High oxygen abundance means many generations of massive stars have already completed their life cycle. For an early galaxy to show high oxygen abundance, it must have already run through a rapid sequence of stellar generations, each one forming, burning through its fuel in millions of years, exploding, enriching the surrounding gas, and triggering the next generation. Multiple cycles, all compressed into an impossibly short window. The chemical evidence aligns with and strengthens every other line of evidence Webb has accumulated. The mass problem, the brightness problem, the structural maturity problem, all point at the same underlying reality. The early universe ran its stellar chemistry at a pace the model does not accommodate. Some researchers point to the population 3 stars discussed earlier as the accelerant. Those enormous, short-lived first-generation stars would have produced and released heavy elements on a dramatically compressed timescale compared to modern stellar populations. A generation of population 3 stars living and dying within 10 million years could have enriched surrounding gas to levels that would take billions of years to reach through normal stellar evolution. This is a plausible theoretical framework. Population 3 enrichment has the chemical head start that explains what Webb is reading in early galaxy spectra. But it requires population 3 stars to have existed in large numbers, formed quickly, and died violently, all in the first 100 million years of cosmic time. That is a dramatic claim. Plausible, supported by a theory consistent with the data, but unconfirmed by direct observation. And the chemical evidence carries one more layer of strangeness, because one of the byproducts of stellar death is something that should have been nearly absent in the early universe, something that requires destruction to create, something whose presence in early galaxies deepens the mystery by yet another degree. Dust. Dust sounds mundane. In the context of the early universe, it is extraordinary. Cosmic dust is not the fine household particles you brush off a shelf. It is composed of tiny solid grains, a few millionths of an inch across, made of silicates, carbon compounds, and other heavy materials. It forms in the cooling outer layers of dying stars, and in the dense debris clouds left behind by supernovae. It absorbs ultraviolet light and re-radiates it as infrared. It is the raw material from which planets form. Without cosmic dust, there are no rocky planets, no chemistry complex enough for biology, and almost certainly no life. Here is the critical fact: dust requires heavy elements to form. You cannot build a silicate grain from hydrogen and helium. You need silicon, oxygen, carbon, iron. All of these are stellar products. All of them require generations of stars to live and die. In the early universe, dust should have been nearly absent. The first billion years of cosmic time should have been a dust-free epoch, with only the cleanest primordial gas, and whatever trace enrichment the first stellar generations had managed to produce. Webb found dust in galaxies less than 1 billion years old. Several early galaxies in Webb's survey data showed clear infrared signatures of significant dust content. One analysis identified a galaxy at roughly 700 million years after the Big Bang, containing a mass of dust equivalent to tens of millions of times the mass of our own star. A vast quantity of solid, heavy element-rich material, already accumulated and distributed through a galaxy that had barely had time to exist. The production rate problem is severe. Forming that quantity of dust requires a corresponding quantity of heavy elements. Producing those heavy elements requires a corresponding number of stellar deaths. Each supernova produces only a fraction of that dust quantity. To accumulate the observed dust mass in under 700 million years demands a supernova rate that strains credibility under standard stellar evolution models. Some researchers have proposed that asymptotic giant branch stars, a class of evolved medium-mass stars in their final phase, could be significant dust producers in the early universe. These stars are efficient dust factories and operate on somewhat shorter timescales than previously appreciated. Including them in early universe chemical models helps close the gap partially. Others point again towards population 3 stars. Their extreme masses would have produced correspondingly extreme amounts of heavy elements in their death explosions. A generation of population 3 supernovae could have seeded the surrounding gas with enough material to explain the dust masses Webb is measuring. Neither explanation is yet confirmed as sufficient on its own. The dust problem remains an open and active research question, but it adds a third chemical constraint alongside the oxygen abundance and the evolved stellar populations. 3 independent chemical signals, all pointing at the same conclusion. The early universe ran through stellar generations rapidly, in ways that produce chemical complexity far ahead of schedule. And the weight of that evidence, chemical, structural, and mass-based, has pushed some researchers toward a question that would have seemed professionally dangerous to ask just a decade ago. What if the universe is older than we think? The age of the universe is one of the most precisely measured numbers in all of science: 13.8 billion years. Derived from multiple independent methods, the rate of cosmic expansion measured across thousands of galaxies, the temperature and pattern of the cosmic microwave background, the ages of the oldest stars in globular clusters, and the abundances of light elements produced in the Big Bang. All of these converge on the same answer within a narrow margin. It is one of the most robust results cosmology has ever produced. And yet, a small but growing number of researchers have begun asking whether that age might be wrong. Or more precisely, whether the universe as we measure it today could represent a phase of something older, and whether Webb's impossible early galaxies are pointing toward a cosmic history that began before the event we call the Big Bang. This is a minority position, firmly in theoretical territory, but it is being advanced by credentialed researchers in peer-reviewed publications, so it deserves honest examination. The argument runs as follows. The standard age measurement assumes lambda CDM correctly describes the full history of the universe from the Big Bang onward. If lambda CDM is wrong in certain details, those details could affect the inferred age. Some alternative cosmological models, particularly those that modify how dark energy behaved in the early universe, produce slightly different age estimates. A few produce significantly different ones. One proposal, advanced seriously in recent years, suggests the universe could be as old as 26.7 billion years, nearly double the standard estimate. This claim comes from a specific alternative model that interprets galaxy evolution data differently and proposes a longer cosmic history. The mainstream reaction has been skeptical. Most cosmologists consider the cosmic microwave background data alone sufficient to anchor the 13.8 billion year estimate firmly. But the proposal highlights that the age question and the early galaxy question are connected. If the universe is older than currently measured, the impossible galaxies become less impossible. They had more time. The timelines relax. The challenge is that changing the age of the universe requires explaining why the cosmic microwave background appears to indicate a younger universe. That background is the afterglow of the Big Bang itself, and its pattern and temperature encode the age of the universe at the time of emission. Changing the age requires reinterpreting that pattern, which requires modifying the physics of the early universe in ways that must remain consistent with all other observations. No alternative model has yet managed that reinterpretation without breaking something else. So the age question remains open at the theoretical edges, firmly settled at the mainstream center. What Webb has done is give the theoretical edges new and specific observational ammunition. And directly connected to the age question is a deeper one, the one researchers rarely said out loud until recently. A question about what, if anything, came before everything. Cosmology has a standard answer for the question of what came before the Big Bang. The answer is that the question may not have meaning. Time itself, according to general relativity, emerged with the Big Bang. Asking what came before is like asking what is north of the North Pole. The coordinate system breaks down before you get there. That answer has always been philosophically uncomfortable, and Webb's findings have given researchers on multiple theoretical fronts new reasons to push past it. Two major theoretical frameworks address the pre-Big Bang question, and they reach opposite conclusions about what Webb's early galaxies imply. The first is cosmic inflation, the dominant theory of the very early universe. Inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing by an incomprehensible factor in an incomprehensibly short time. This expansion smoothed out the early universe to the uniform state we observe in the cosmic microwave background, generated the small density fluctuations that seeded all structure, and solved several other theoretical problems that a non-inflationary Big Bang could not address. Under inflation, the Big Bang was the beginning. Nothing preceded it in any physically meaningful sense. Webb's early galaxies challenge inflation indirectly, because the density fluctuations inflation generated are supposed to define the initial conditions for all structure formation. If those initial conditions are insufficient to produce the structures Webb is observing, the inflationary parameters need revision. Some researchers are now working to determine whether modified inflationary models can produce the initial density fluctuations required to seed Webb's early structures. The second framework is cyclic cosmology. Under certain cyclic models, the Big Bang was a transition between a previous phase of the universe and the current one, a bounce, a collision between higher dimensional structures, or a phase transition in a pre-existing spacetime. The universe we inhabit is one cycle in an ongoing sequence. Structures from previous cycles could theoretically influence the starting conditions of the current one, potentially providing a head start for early galaxy formation. Cyclic cosmologies remain highly speculative. There is currently no confirmed observational signature that distinguishes a cyclic universe from a standard inflationary one. Webb's early galaxy findings have been cited by proponents of cyclic models as circumstantial support, since a pre-existing cosmic heritage could explain why structure appeared so early. But circumstantial is the operative word. The claim is theoretical extrapolation, not confirmed evidence. What is confirmed is that the very earliest observable epoch of the universe, the one Webb is now probing directly, contains surprises significant enough to force theorists on all sides to revisit their foundations. The instrument doing the probing deserves a closer look, because the reason Webb sees things Hubble never could is not just a matter of a bigger mirror, it is a matter of a completely different kind of vision. For 3 decades, the Hubble Space Telescope was humanity's deepest eye. It showed us galaxies billions of light years away. It measured the expansion of the universe with precision that reshaped cosmology. Its deep field images, taken by pointing at a seemingly empty patch of sky for days or weeks, revealed thousands of distant galaxies and became some of the most celebrated scientific images ever captured. Hubble saw primarily invisible and ultraviolet light, with some near-infrared capability added through later servicing missions. For the vast majority of cosmic history, that was sufficient. But the most distant universe, the first billion years, sits beyond Hubble's reach for a specific physical reason. The universe is expanding. As it expands, light from distant objects stretches. The further the object, the more the light stretches. For objects at the distances where the early universe lives, the light has stretched so far that it exits the visible spectrum entirely and shifts into infrared wavelengths. By the time light from a galaxy at redshift 10 reaches us, it is invisible to human eyes and to any telescope designed primarily for visible light. Hubble was built for the visible universe. The early universe speaks in infrared. That gap is absolute. No tuning of Hubble's instruments could bridge it. The early universe was simply outside Hubble's physical language. Its primary mirror spans roughly 21 feet, about 2.5 times the collecting area of Hubble's mirror. Larger mirrors collect more light, which means fainter objects become detectable. But the mirror size is almost secondary to the instrument design. Every detector on Webb is tuned specifically for infrared wavelengths. Its sunshield, a 5-layer structure the size of a tennis court, blocks heat from the Earth, Moon, and star to keep the telescope cold enough that its own thermal glow does not overwhelm the faint infrared signals it is hunting. Webb operates at roughly negative 448 degrees Fahrenheit, just 40 degrees above absolute zero. At that temperature, the telescope itself stops being a source of infrared noise. The result is a telescope that can detect infrared sources roughly 100 times fainter than anything Hubble could see in that wavelength range. 100 times. That is the difference between seeing a distant campfire and detecting the warmth of a single candle at the same distance. When Webb looked at the same patches of sky Hubble had studied for decades, it found objects Hubble had no capacity to detect. Galaxies at redshifts of 8, 10, 12, 14, and beyond appeared in Webb's data like suddenly visible stars emerging after your eyes adjust to the dark. The transition from Hubble to Webb was not an incremental improvement. It was a categorical shift in observational capability, comparable to the shift from the naked eye to the first optical telescope. A door opened into a previously invisible era of cosmic history. And through that door came every impossible galaxy discussed in this story. Not because the galaxies were new. They had been sitting there for billions of years, emitting their infrared light into space. They were impossible to see before Webb. Now they are impossible to ignore. The most chemically extreme of them, one specific galaxy whose spectral data forced a rewrite of stellar evolution timelines, illustrates just how severe the revision needs to be. It did not announce itself dramatically. It appeared in Webb's survey data as a compact, relatively bright source at an extreme redshift. Standard procedure: flag it, add it to the spectroscopic follow-up queue, wait for confirmation. When the spectroscopic data came back, the research team ran their analysis expecting the usual result. A young galaxy, modest chemical enrichment, broadly consistent with the standard model, perhaps slightly ahead of schedule. Instead, the spectrum showed oxygen and carbon abundances approaching the levels observed in galaxies in the nearby universe. Galaxies with over 10 billion years of chemical history behind them. This particular galaxy existed at a time when the universe was under 500 million years old. The chemical enrichment level required working backwards through stellar evolution models, demanded a history of intense star formation, running across multiple complete stellar generations, each cycle producing, dispersing, and reincorporating heavy elements into new stars. The minimum elapsed time for that chemical history, using the most aggressive star formation rates the models allow, pushed uncomfortably close to the age of the universe at the time of observation. Some analyses suggested the chemical history implied by the spectrum may have required more time than the galaxy had existed. That sentence deserves to sit alone for a moment. The chemical record inside the galaxy pointed to a history longer than the galaxy's confirmed age. Like reading tree rings in a sapling and counting more rings than years the tree has been alive. The research team considered instrumental effects. They checked for contamination in the spectrum. They reran the stellar population models with different input parameters. They tested whether an unusual initial mass function, a distribution of stellar masses skewed heavily toward the most massive stars, could compress the enrichment timeline sufficiently. The massive star scenario helped. Galaxies dominated by very massive, short-lived stars produce and disperse heavy elements faster than normal stellar populations. This is the population 3 connection again, suggesting that the very first stellar generations in this galaxy were dominated by extreme mass stars that lived and died in compressed timeframes. Even with that correction applied, the chemical timeline remained tight, barely consistent with the available time, and only under the most aggressive assumptions. When the team published, the paper was careful in its language. They did not claim to have found a galaxy older than the universe. They described their results as requiring either extremely efficient early star formation, dominated by very massive stars, or a revision of stellar nucleosynthesis models at low metallicity, meaning under chemically pristine conditions. Both revisions are significant. Both have implications that ripple outward through multiple areas of astrophysics. And this galaxy was not unique. It was the most extreme confirmed case in a distribution of early galaxies showing elevated chemical maturity. The distribution itself is the signal. Outliers are expected. A systematic trend toward chemical overmaturity across hundreds of early galaxies is evidence of a process that operated differently in the early universe. That process left another signature, one that does not involve chemical abundance at all, one that involves raw, blinding, ultraviolet light. Ultraviolet light is the radiation of youth. Young, massive, hot stars pour ultraviolet radiation into space at rates that older, cooler stellar populations cannot match. When a galaxy is actively forming large numbers of massive young stars, it blazes in ultraviolet. When star formation slows or stops, that ultraviolet glow fades. Astronomers use ultraviolet brightness as a direct tracer of current star formation activity. The relationship between a galaxy's ultraviolet output and its star formation rate is one of the most calibrated tools in observational astronomy. It has been tested across thousands of galaxies at many different cosmic distances. The calibration holds, the relationship is reliable. Webb found early galaxies producing ultraviolet radiation at rates that the calibrated relationship says are impossible given their estimated masses. This is called the ultraviolet luminosity excess, and it is one of the most statistically robust problems Webb has delivered to cosmology. It appears across large galaxy samples. It is not driven by a handful of unusual outliers. It is a systematic offset. Early galaxies at high redshift producing more ultraviolet light than their stellar mass should allow, persisting across the full range of distances Webb has surveyed in the early universe. The magnitude of the excess in some cases reaches a factor of 10. A galaxy producing 10 times the ultraviolet output expected for its mass is not a calibration error. It is a statement that either the mass estimates are dramatically wrong, or the stars inside these galaxies are producing light in a fundamentally different way. 3 physical explanations have been seriously proposed. The first returns to population 3, and extremely massive stars. As discussed, stars with masses hundreds of times greater than typical stellar masses produce ultraviolet radiation with extraordinary efficiency. A galaxy whose stellar population is dominated by such extreme mass stars would show exactly the kind of ultraviolet excess Webb is measuring. This explanation is theoretically consistent, but awaits direct confirmation. The second involves active galactic nuclei, supermassive black holes in the process of actively feeding. An actively feeding black hole produces enormous quantities of ultraviolet and higher energy radiation from the superheated disk of infalling material around it. If a significant fraction of the early galaxies Webb observes have active central black holes, their ultraviolet output would be boosted above what stellar populations alone could produce. Webb has confirmed active galactic nuclei in several early galaxies. Whether the fraction is large enough to explain the full ultraviolet excess across the population is still being determined. The third explanation is the most structurally challenging for the Standard Model. It proposes that the initial mass function itself, the distribution of stellar masses that forms in any given burst of star formation, was fundamentally different in the early universe. An early universe initial mass function skewed toward very high stellar masses would naturally produce populations that generate far more ultraviolet light per unit of total mass. If the initial mass function was different early on, it means the basic rule governing how stars form changed over cosmic time. That is a significant revision to stellar physics, one that would propagate changes through essentially every area of galaxy evolution theory. The ultraviolet excess is confirmed, the cause is actively debated. And whatever the cause turns out to be, it connects directly to what was happening between galaxies in the early universe, in the spaces where galaxies were meeting, colliding, and feeding each other at a rate nobody predicted. Galaxies are not isolated islands. They interact, they pass through each other, distorting shapes and triggering star formation. They collide and merge, combining their mass into larger systems. They strip gas from each other through gravitational tides. Galaxy interactions are a fundamental driver of evolution, and their frequency determines the pace at which the universe builds larger and more massive structures. Under lambda CDM, the galaxy merger rate peaks at around 2 to 3 billion years after the Big Bang, and declines as the universe expands and galaxies spread further apart. The early universe, before that peak, is predicted to have a lower merger rate because galaxies are still forming and the large-scale structure is still assembling. Webb observed the opposite. Multiple survey programs using Webb's imaging found galaxy pairs, interacting systems, and merger candidates at rates significantly exceeding lambda CDM predictions at early cosmic times. One study examining galaxies in the first 2 billion years found a merger fraction roughly 3 to 5 times higher than the model's predictions for that era. A higher merger rate in the early universe has compounding consequences. Mergers between gas-rich galaxies trigger intense bursts of star formation. The gravitational disruption compresses gas clouds, overwhelming the thermal pressure that keeps them from collapsing, and igniting stellar nurseries across both merging systems simultaneously. A galaxy experiencing a major merger can temporarily form stars at rates 10 to 50 times its typical baseline, a phenomenon called a starburst. If early galaxies were merging more frequently than predicted, they were triggering more starbursts, more frequently across a larger fraction of the cosmic volume. This provides a natural accelerant for the rapid mass assembly Webb keeps documenting. It also affects the central black holes. Galaxy mergers drive gas toward galactic centers, feeding central black holes and triggering active galactic nucleus activity. A universe with a higher early merger rate would produce more rapidly growing black holes at early times, which connects directly back to the oversized black holes Webb has confirmed. The merger rate discrepancy is real and confirmed across multiple independent programs. The explanation within the Standard Model requires adjusting the initial density fluctuations to produce a more clustered early universe, meaning galaxies were more likely to find each other and interact because they were born closer together than the model predicted. This clustering adjustment, like the dark matter halo efficiency adjustment discussed earlier, requires modifying the initial conditions of the universe. The conditions immediately following the Big Bang, encoded in the cosmic microwave background, would need to have been slightly different from their measured values to produce the observed clustering. That difference is small enough that the cosmic microwave background data cannot definitively rule it out. But it is a revision, one more place where the Standard Model needs to bend to accommodate Webb's observations. And there is one specific early galaxy that bends the model in a direction nobody expected. Because while most early galaxies show signs of dark matter doing exactly what the model predicts, one showed almost none at all. Dark matter is supposed to be everywhere. The standard model treats dark matter as the skeleton of all cosmic structure. Every galaxy sits inside a dark matter halo. The halo predates the visible galaxy, forms faster than ordinary matter can organize itself, and provides the gravitational well into which gas eventually falls. Remove the dark matter halo, and there is no gravitational seed around which a galaxy can form. No halo means no galaxy. That is the standard picture. It is held up across virtually every observation conducted over decades. Webb found an early galaxy that appears to violate it. The galaxy, confirmed at a distance placing it in the first 2 billion years of cosmic history, showed rotation and velocity measurements inconsistent with a massive dark matter halo. When astronomers measured how the stars inside this galaxy were moving, and compared those velocities to what a standard dark matter halo would predict, the numbers did not match. The stars were moving as though most of the mass inside the galaxy was the visible stellar mass alone, with far less dark matter than the model demands. In the local universe, similar dark matter-poor galaxies have been found, and they generated significant controversy. The prevailing explanation for those local cases involves tidal stripping, where a nearby massive galaxy gravitationally pulls dark matter out of a smaller companion over billions of years, depleting its dark matter halo. For an early galaxy at this redshift, the tidal stripping explanation is harder to apply. The universe at that age was not old enough for the long, slow process of tidal stripping to have depleted a full dark matter halo. The galaxy would need to have formed with very little dark matter from the beginning. That possibility challenges a fundamental assumption. If some galaxies can form and exist with minimal dark matter halos, the role of dark matter in galaxy formation is more complicated than the model assumes. Either dark matter distributes itself unevenly in the early universe, in ways current models do not capture, or some other mechanism can substitute for the gravitational anchoring dark matter is supposed to provide. Some researchers have proposed modified theories of gravity as an alternative framework. Under certain modified gravity models, ordinary visible matter produces stronger gravitational effects at low accelerations than standard gravity predicts, potentially removing the need for dark matter in some regimes. These models have had mixed success explaining other observations, and remain controversial. The early dark matter poor galaxy is a confirmed anomaly. The explanation is actively contested, and it deepens the already substantial pressure on the standard model from a completely new direction. The behavior of dark matter itself, under early universe conditions, may have been different from current assumptions. That possibility connects to a theoretical proposal that has gained significant traction as cosmologists try to reconcile Webb's findings with the existing framework without abandoning it entirely. A proposal that adds a new ingredient to the universe's energy budget, specifically tuned to operate in its earliest chapters. Dark energy is the force driving the universe's accelerating expansion. It was discovered in the late 1990s through observations of distant supernovae, and its existence is confirmed by multiple independent measurement methods. In the standard model, dark energy is a constant property of empty space, a fixed energy density that does not change over time, and has been present at the same level throughout cosmic history. That constancy is an assumption, a well-motivated one, but still an assumption. Some cosmologists have proposed that dark energy was different in the early universe. Specifically, that there was an additional component of dark energy that was active only during the first million years or so of cosmic history, and then diluted away, leaving the universe with only the constant dark energy component we observe today. This hypothetical component is called early dark energy. The original motivation for early dark energy had nothing to do with Webb's galaxies. It came from a different crisis in cosmology, the Hubble tension. But early dark energy, introduced to address the Hubble tension, turns out to have interesting side effects on early galaxy formation. By modifying the energy content of the early universe, early dark energy models alter the rate at which density fluctuations grow into structure. In some versions, the modification produces faster early structure growth, which would allow dark matter halos to build mass more quickly, giving galaxies a head start on assembly. This makes early dark energy a candidate solution for multiple Webb-related problems simultaneously. It could, in principle, explain the accelerated galaxy formation, the early cluster, the the oversized black holes, and the ultraviolet luminosity excess, all within the existing mathematical framework of cosmology. By adjusting the energy content of the early universe, rather than revising galaxy formation physics directly, the proposal is compelling as a unifying explanation. It is also currently unconfirmed. Observational constraints on early dark energy are significant. The model must remain consistent with the cosmic microwave background, with nucleosynthesis, and with the large-scale structure of the intermediate distance universe. Several versions of early dark energy have been ruled out or severely constrained by these tests. The versions that survive are narrow and require careful parameter tuning. Webb itself is contributing to the early dark energy tests. By measuring the galaxy population across a range of early universe epochs with high statistical precision, Webb is providing the observational data against which early dark energy predictions can be checked. Some versions of the model make specific, testable predictions about galaxy abundance and properties that Webb is now in a position to verify or falsify. The tension between the standard model and Webb's observations does not exist in isolation. It connects to other cracks in the cosmological framework that were already there before Webb launched. And the deepest of those cracks runs through the measurement of the universe's expansion rate itself. There are two ways to measure how fast the universe is expanding. The first looks backward. Astronomers analyze the cosmic microwave background, the ancient light released 380,000 years after the Big Bang, and use the pattern of temperature fluctuations embedded in it to calculate the expansion rate of the universe. This method anchors itself firmly in the early universe. It produces a precise number. The second looks around. Astronomers measure the distances to nearby galaxies using standard candles, objects with known intrinsic brightness, and compare those distances to the galaxy's recession velocities. The relationship between distance and recession speed gives the current expansion rate directly. This method anchors itself in the local universe. It also produces a precise number. The two numbers disagree. The disagreement is not within measurement uncertainty. Both measurements have been refined and cross-checked extensively over the past decade. The gap between them has grown more significant with each refinement, not less. The early universe measurement produces a lower expansion rate. The local measurement produces a higher one. The discrepancy is roughly 8 to 9%. In physics, an 8% disagreement between two measurements of the same thing, both conducted carefully and cross-checked independently, means something is wrong somewhere. Either one of the measurements has a systematic error that has not yet been identified, or the standard model is missing something that behaves differently in the early versus the late universe. This disagreement is the Hubble tension, and it has been the most acute, unresolved problem in cosmology for nearly a decade. Webb is relevant to the Hubble tension in two ways. First, Webb has been used to independently verify the local distance measurements, specifically checking whether the standard candles used in those measurements, a class of pulsating stars called Cepheid variables, have been correctly calibrated. Early Webb results confirmed the Cepheid calibrations used by previous teams, strengthening the case that the local measurement is correct, and the tension is real. Second, Webb's early galaxy findings suggest the early universe was more structured and active than lambda CDM predicts. If the early universe had higher than expected dark matter halo growth, or early dark energy, or modified initial conditions, those same modifications would affect the expansion rate the early universe measurement infers from the cosmic microwave background. Some proposed solutions to the Hubble tension predict specific changes to early universe structure formation that Webb could test directly. The galaxy population Webb observes at high redshift either matches or fails to match those predictions. Webb is therefore not just a passive observer of the tension, but an active tool for resolving it. The Hubble tension and the early galaxy problem are facets of the same deeper issue. The standard model, extremely successful across an enormous range of scales and epochs, is showing cracks at both ends of cosmic time. At the early end, galaxies form too fast. At the late end, the universe expands too fast. Something threading through the entire history of the universe needs revision. That revision may involve physical constants we have always assumed were fixed. constants that may have been, in the earliest moments of cosmic history, meaningfully different from the values we measure today. Physics rests on a foundation of constants: the speed of light, the strength of gravity, the rate at which atomic nuclei interact, the fine structure constant governing how charged particles and electromagnetic radiation interact. These numbers are measured with extraordinary precision in laboratories and in astrophysical observations. They appear to be the same everywhere we have tested them, across the observable universe and across cosmic time. That universality is a foundational assumption of all physics. Constants are constant. They do not vary in space. They do not change over time. Every equation in cosmology, every simulation, every model of galaxy formation relies on this assumption. What if it is wrong? Several independent theoretical frameworks propose that some constants might have had slightly different values in the extreme conditions of the early universe, not arbitrary variation. Specific, physically motivated changes arising from the interaction of fundamental fields during a high-energy early phase that later settled to their current values as the universe cooled and expanded. The constant most actively discussed in this context is the fine structure constant, which governs the strength of electromagnetic interactions. Some theoretical models predict it was slightly different in the early universe, and astronomical observations of quasar absorption lines have hinted at possible variation at the level of a few parts per million across cosmic time. These hints are not confirmed. They remain tantalizing and contested. More directly relevant to Webb's findings is the effective star formation constant. The rate at which gas converts to stars in a collapsing cloud depends on the interplay of gravity, thermal pressure, magnetic fields, and turbulence. All of these involve physical constants. If any of those constants were slightly different in the early universe, star formation could have been fundamentally more efficient than today, not because of unusual conditions, but because the underlying physics operated differently. This idea is deeply speculative and lacks direct observational support. It is worth mentioning not as a likely explanation, but as an illustration of how far the theoretical investigation has been forced to reach. What is confirmed is that the standard assumption of constant physical constants produces predictions that conflict with Webb's observations. Whether the resolution involves varying constants, modified dark matter, early dark energy, revised initial conditions, or some combination remains entirely open. The scientific process demands that confirmed observations take precedence over theoretical expectations. Webb's observations are confirmed. The theoretical expectations they conflict with are, consequently, in the process of revision. The question is how deep that revision will go. Some researchers argue the answer is not very deep. Moderate adjustments within lambda CDM will suffice. Others argue the answer requires rebuilding from the foundations upward. The implications of that second possibility extend far beyond astronomy. A fundamental revision to our understanding of the universe's origin and structure would reshape physics, philosophy, and every answer we thought we had to the deepest questions about where everything came from. And Webb has already found galaxies that even the revised models cannot explain. Let us be precise about what is and is not at stake. The standard model of cosmology, lambda CDM, is a framework, a highly successful one, built from decades of observations and confirmed by an enormous body of evidence. The findings Webb has produced do not erase that evidence. They add to it. They reveal that the framework, accurate and predictive across a vast range of scales, breaks down or requires significant modification at the extreme early end of cosmic history. If the standard model requires fundamental revision rather than moderate adjustment, the consequences run deep. The most immediate consequence is conceptual. Our understanding of how the universe began and evolved is one of the defining intellectual achievements of the 20th century. It underpins every field that connects to cosmology, particle physics, stellar astrophysics, planetary science, and even, at the farthest reaches, astrobiology. A fundamental revision to the cosmological framework propagates through all of those fields. Specific practical consequences follow. The timeline of heavy element production is central to understanding how quickly rocky planets can form in the universe. If early galaxies ran through stellar generations faster than currently modeled, Heavy elements were available in the cosmic medium earlier than we thought. That means rocky planets could have formed earlier in cosmic history, which means complex chemistry, and potentially life, may have had far more time than current models suggest to emerge, not just on Earth, but across the universe. The nature of dark matter, already the most significant known unknown in physics, comes under even greater scrutiny if early galaxies reveal it behaving differently at extreme redshifts. Every proposed dark matter experiment, every detector searching for dark matter particles in underground laboratories operates on assumptions about what dark matter is and how it behaves. Revise those assumptions, and the experimental strategies may need to follow. The Hubble tension, if resolved by a revision to early universe physics, could point toward new particles, new fields, or new interactions that extend beyond the standard model of particle physics. The two standard models, cosmological and particle physics, are deeply intertwined. A crack in one tends to propagate toward the other. Most fundamentally, a confirmed revision to our cosmological origin story forces a confrontation with the question of initial conditions. What set up the Big Bang to produce the universe it produced? If those initial conditions were different from what lambda CDM assumes, why? What physics governs those conditions? And can we ever observe evidence of what, if anything, preceded them? Webb is not answering those questions. It is sharpening them to a point where they can no longer be set aside. And it is doing so by finding specific, confirmed objects that no version of the current framework can explain. The galaxies for which even the revised models produce no satisfactory answer. Most of Webb's impossible galaxies are impossible in the sense that they push the standard model significantly beyond its comfort zone. They require modifications, adjustments, revised parameters. They are, with effort, accommodatable within some version of an updated lambda CDM. A handful are not. Among the thousands of early galaxies Webb has catalogued, a small subset stands apart. They are the cases where the combination of confirmed distance, confirmed mass, confirmed chemical maturity, and confirmed structural complexity stacks high enough that even the most aggressively revised models produce no satisfactory explanation. One category involves galaxies at extreme redshifts with stellar masses so large that producing them within any lambda CDM variant, however modified, would require conditions that violate other confirmed observational constraints. Every proposed fix for the mass problem encounters a constraint somewhere else in the data that breaks the fix before it can be applied. These are not cases where the data is uncertain. The redshifts are spectroscopically confirmed. The mass estimates, while carrying uncertainties, have been independently cross-checked using multiple methods. The constraints they violate are themselves confirmed by independent observations. Every exit from the problem closes before you reach it. A second category involves the combination of structural maturity and chemical complexity in the same object. Individual galaxies showing extreme chemical enrichment can be explained by invoking unusual stellar populations. Individual galaxies showing unusual structural maturity can be attributed to rare formation pathways. But galaxies showing both simultaneously, at confirmed extreme distances, strain every proposed explanation to breaking point. For these objects, the response from the cosmological community has been honest. Some papers use language like, currently inexplicable within existing frameworks. Others flag them as priority targets for follow-up observations, not because better data will make the problem disappear, but because the better data might reveal a new physical mechanism that could absorb the anomaly. That is the scientific response at its best. Acknowledge what the data says. Acknowledge that no current explanation works. Search for new physics rather than forcing the data into an inadequate model. The honest answer, as of the current state of the field, is that a small but significant fraction of Webb's most extreme early galaxy discoveries cannot be explained. They are real, they are confirmed, and they are waiting for a theoretical framework capable of containing them. And Webb is not finished. The telescope has a designed operational lifetime of at least 20 years. It has been in operation for a fraction of that time. The survey programs underway represent a small portion of what the instrument is capable of delivering. The follow-up spectroscopic programs, gathering the precise chemical and kinematic data needed to confirm or revise the most extreme candidates, are still accumulating. Every month, new data arrives. Every month, the picture of the early universe sharpens. Webb is pointing at the edge of everything. Right now, as you listen to this, the telescope is 230 miles per hour in the wrong direction to catch with the spacecraft. Drifting in its gravitational equilibrium point a million miles from Earth, gathering infrared photons that have been traveling for over 13 billion years. Some of those photons left their sources before the Earth existed, before our star existed, before half the stars visible in the night sky were born. The current observational programs include some of the most ambitious deep field surveys ever attempted. One program is accumulating hundreds of hours of exposure time on a small patch of sky, building toward a dataset an order of magnitude deeper than the first Webb deep field images. At those depths, the expectation is to push confirmed galaxy detections to redshifts of 15, 16, possibly higher, corresponding to cosmic times under 250 million years after the Big Bang. Nobody knows exactly what will appear at those distances. The standard model predicts essentially nothing. At redshift 15, the universe was so young that even the accelerated galaxy formation Webb has documented at lower redshifts should not yet have produced detectable objects. The model's predictions, even in their revised forms, fade towards zero at these extreme distances. Webb has a history of finding things where models predicted nothing. A separate program is targeting candidate population 3-star signatures in existing data, pursuing the objects identified as the most likely hosts of first-generation stellar populations. Confirmation of population 3 stars would rank among the most significant astrophysical discoveries ever made. It would close the last direct observational gap in the story of stellar evolution, from the first starlight to the complex stellar chemistry that built the atoms in your cells. Another program is mapping the large-scale structure of the early universe across a wide field, building a three-dimensional picture of how galaxies, dark matter, and cosmic filaments were arranged in the first 2 billion years. This map will either confirm or challenge the clustering predictions that several competing cosmological models make at these early times. It is, in effect, a direct test of the initial conditions of the universe. And Webb is gathering in parallel the spectroscopic data needed to resolve the most extreme galaxy candidates that photometric surveys have flagged over the past 3 years. For each confirmed impossible galaxy that has forced a revision to the theoretical framework, there are dozens of candidates awaiting the precise measurements that will confirm or refine them. The history of this telescope, even in its short operational life, is a history of the universe being stranger than anyone predicted. Every time cosmologists adjusted their expectations and looked again, Webb found something further outside those expectations. The pattern has been consistent enough that the most honest prediction for what comes next is simply this: whatever it is, the models did not see it coming. The universe began in conditions we do not yet understand, structured itself in ways our best theories still struggle to reproduce, and has been filling a telescope we built in blind faith with images that shake the foundations of what we thought we knew. We are watching a field rewrite itself in real time, galaxy by galaxy, redshift by redshift, one confirmed impossibility at a time. Webb keeps looking, and the early universe keeps answering in a language we are only beginning to learn.